Welcome to our presentation on data type agnostic visual sensitivity analysis. In many domains, analysts deal with multivariate spatial data. Spatial blind source separation, SBSS in short, is a model explicitly designed for spatial data analysis. It is superior to popular non-spatial methods, like principal component analysis. The main challenge in SBSS is setting to complex tuning parameters, the regionalization, and the kernel specification. The first parameter, regionalization, is a partition of location into coherent regions. The second parameter, the kernel, defines the extent of a location's neighborhood. Both parameters and the model's output are spatial objects and need to be considered as such. Sensitivity analysis compares the relative variation of parameter settings and output. It is interesting in general but can also support other tasks, such as optimization. Here is how one could do visual sensitivity analysis of a model with two parameters, in green, and one output, in purple, using a parallel coordinates plot. When the outputs are more widely distributed than the parameter settings, we have found a sensitive subrange of the parameter. Similarly, when the outputs are more narrowly distributed than the parameter settings, we have found a stable subrange of the parameter. If no pattern exists, the parameter is likely relevant, as for P1. However, to do the same analysis in SBSS, the main challenge we faced was what to do when neither parameters nor outputs are numbers but geospatial objects. For this reason, we propose a visual analytics, short, VA, approach to support sensitivity analysis in case of complex parameters and output. Our contributions are that we propose a task abstraction for sensitivity analysis in the context of SBSS. We develop a VA prototype that supports sensitivity analysis and works on any data type. We evaluate the prototype with experts in visualization and SBSS. Finally, we demonstrate the transferability by applying our approach to microclimate simulations. To clarify the requirements of our primary users, we identified several tasks through extensive literature analysis and a user-centered design process with our collaborators, who are statistics experts. Our anticipated users include experts in statistics and application domain experts, for example, from geochemistry or microclimate simulation. First, analysts must compare the association between parameters and outputs, T1, to start the analysis. For any given parameter or output, they must assess its overall variation, T2, to learn about contained similarity structures and outliers. Furthermore, analysts must identify groups of data cases with low or high variation in a parameter or output, T3, in order to compare variation between parameters and outputs, both overall and for a group of data cases, T4. To support analysts in reasoning why this variation happens, they must be able to view individual data cases, T5. The basic idea in our approach is to use difference in cluster diameters as a measure of variation. It works like this. We start with the complex parameters and outputs. We require dissimilarity measures for each of those. We assume to have any number of tuples, including parameter and output combinations. Next, we do a bottom-up hierarchical clustering for parameters and outputs separately. Any non-flat clustering works here. We chose bottom-up because it's simple to explain and implement. The advantage of hierarchical clustering is that we find all clusters and can enumerate them. Next, we make cluster diameters comparable by min-max normalization or ranking. After that, we can enumerate clusters in the parameter space and calculate the diameter difference compared to the output space. or the other way around. Sensitive parameter ranges are characterized by wider clusters in the output space, and stable ranges vice versa. We visualize the cluster diameter difference by color hue in a dendrogram, which we call a discrepancy dendrogram. This image shows the VA prototype with an SPSS dataset. In the center is the discrepancy dendrogram that is constructed based on cluster diameter differences like illustrated before. We provide several interactions with the discrepancy dendrogram to allow detailed investigation of clusters. The gallery view to the right shows the selected cluster's content in domain-specific visualizations. Details are available on demand in a tooltip. In this case, the gallery shows ring-shaped kernel parameter settings and the tooltip an interactive map. To the left are controls to change visualization parameters. Rank or min-max normalization, complete or average linkage, and color scale. Additionally, there are small visualizations to assist navigation, like the Shepherd matrix and the subset sensitivity view. The matrix of Shepherd diagrams shows the association between two variables and gives analysts a way to judge which parameter output relations to investigate. Dispersed Shepherd scatter plots are more interesting to investigate for the analyst. The subset sensitivity view shows the diameter of the selected cluster in all available parameter and output distances. We thoroughly evaluated our VA prototype in several ways. We applied a heuristic evaluation of our visualization design with visualization experts. We did an expert evaluation with 2 experts in SPSS. Finally, we showed the transferability of our prototype by an expert evaluation with microclimate simulation experts. We followed the ISTE methodology by Wall et al. For the heuristic evaluation. 5 visualization experts answered 21 questions about our visualization design by rating their agreement on a 7-point Likert scale. The average scores per component and in total are greater than the success threshold of 5, therefore our designs can be considered appropriate from a visualization perspective. In the evaluation with 2 SPSS experts, we used meteorological and geochemical datasets, respectively. The slide shows the geochemical dataset with 960 location and 27 variables from Colorado, USA. The parameter settings were chosen by the SPSS expert and the first author of this paper. With the help of our prototype, the SPSS expert could find a sensitive subset of parameter settings. This is because they identified that the blue-marked clusters are broader in output than parameter space. They discovered that regionalization is the more critical parameter because the dendrogram shows output versus regionalization and is gray primarily, plus output clusters were neatly grouped by regionalization. Finally, the 50 km kernel parameter was most stable. Microclimate simulations predict meteorological variables in a small area. This is useful to identify hotspots and simulate ways to cool them. The parameters and outputs are temperature, humidity, and wind. The same building was considered to be constructed in 3 cities. In each city, 4 parameter settings were considered for a total of 12. The investigation aimed to find a target location whilst considering rising temperatures. The findings of the microclimate simulation expert agreed with domain knowledge about physics, for instance, that warmer air is more humid. They also found that wind cannot be used to cool down the building. Additionally, wind speed output was also influenced by temperature input, which the expert could not explain. In the end, Helsinki won because it had the most scenarios in the cluster where output temperature was least dependent on input temperature. Some limitations apply to our approach. The choice of nested partitions depends on the dataset, clustering algorithm, and clustering parameters, and they affect the sensitivity index, visualization, and ultimately the analysis outcome. The visualization image is not guaranteed to be stable with regard to added or deleted data cases, as the sensitivity index depends on the clustering. The sensitivity index is a simple local method, which Saltelli and others argue is appropriate only for linear models. We believe it is still useful for other models because the index is used for visual guidance in an interactive visualization. For future work, we want to support multiple parameters properly, as currently only one parameter can be compared with the output. We also want to find a better mental framework for data type agnostic sensitivity analysis, as two distances/similarities in a group of elements are challenging to grasp. Our approach has parallels to dimension reduction quality metrics, for which often missing or false neighbors are considered. It would be interesting to investigate their relationship with sensitivity analysis more and see if terms or metrics can be generalized, combined, or transferred. Our approach can also be seen as comparing two clusterings made with separate distance metrics, for which we did not find related work. Exploring this more is possible future work for visual cluster analysis. Finally, an issue of our dendrogram representation is that it does not scale to large data sets. Therefore, it would be promising to adapt our approach to dimension reduction scatter plots. Thank you for watching.